Alright guys, I'm going to do a video for 5.3 day 2. So hopefully if you have any questions from homework, the answer key hopefully has answered most of those. So your homework tonight will be homework number 6 on the syllabus, and I'll put the key online and hopefully along with the video that I'm taping right now, which Miss Moore will play for you. So to start off, turn to 5.3 Day 2 Notes. Should have this title. And we're going to start off right away with a formula that's given as average value. And the average value, it's literally coming from the formula for area, basic formula for area. So if you think about the way we've been doing area, we've essentially been doing the integral from b to a of f of x, and the way that we find that, we find the area by doing essentially remember your y-axis unit multiplied by your x-axis unit. So in a sense, we're really doing an area to be a height times a width with a bunch of rectangles, and then we sum them up. So if you look at the average value is actually the height. It's the average height, which is why you get area multiplied, divided by width. So if you look at the formula, it's done by doing area divided by width. Just so you understand that there is a division in here, this here is dividing by width, multiplying by 1 over. And the width of the area would be how wide the shape is. So let's say it looks something like this. So this from a to b is considered the width, and we find the width by doing b minus a. And then the integral of a to b, this piece right here, is the net signed area. So you're actually taking your net signed area and dividing by the width of the interval, and that gets you an average value. So we'll talk a little bit more about what average value is. I'm going to show you what it looks like. So if you look here, we're going to find the average value of this function from 0 to 3 of 1/2 x squared. So the graph of 1/2 x squared is given. The width of the interval is equal to 3 minus 0, which is 3. The integral of 1/2 x squared, so what we're going to do is actually find the integral of 1/2 x squared, and then I'm going to explain graphically what an average value is. So if you remember from homework number 5, you find your you find your average value. So your average, oh my lord, you find your antiderivative is what I meant. So we're going to take 1/2, leave that there. We're going to take the x, we're going to add 1 to the power, and then divide by that same power. So we actually end up with x cubed divided by 6. And then we substitute in 3. And we get 27 over 6, which simplifies to 9 over 2. And then we also get f of 0, which would just be 0 over 6, therefore 0. Sorry that this pen is bleeding. And so the average value would be found by first finding the integral. The integral is 9/2 minus 0, and then the average value, which we'll do by running out of space here, sorry. So I'm going to come on top of the graph. So the average value, that's a symbol for average, and then the value is going to be a y value, would be 1 over the width of the interval multiplied by the integral value, which is 9/2. So the answer becomes 3/2. So I'll show you what that actually means. So 3/2 on this graph would be 1.5. And so first let's start off with showing what the net signed area is. So the net signed area would be the integral. In this case it's positive, and it's this area in pink. The average value would be the y value, where if you take that y value and you create a rectangle, the area of the orange rectangle is equal to the area of the pink integral. And so you can kind of see that the areas are about the same. That is what the average value finds. So if you look at what's written, it says the average value of a function is a value that would give the same area if the function was a constant. So graphically speaking, it gives you the exact same area if you were to kind of melt down the integral into a rectangle. So again, the formula for average value, and we usually write it this way, is equal to 1 over the width of the interval multiplied by the actual integral. All right. So I do want you to know how to do it with the calculator, but I also want to show you that now that we're substituting in real life terms such as velocity and acceleration, there's going to be a little bit confusion. You're going to start to get confused between an average rate of change and an average value. So I'm going to show you the easiest way to figure out which formula to use. So I'm going to write up top the two different formulas you know. You know the average rate of change, and I'm going to bring that down, which is f of b minus f of a all over b minus a. And then now you also know average value, which is 1 over b minus a, integral a to b f of x. So you'll hear the word average twice. So in this case, I want to find the average velocity for part A, and this is the easiest way to figure out which formula you use. You're going to look at the original function that you have, and you're going to look at whose average you're finding. If they are exactly the same, so I'm given velocity, I want average velocity, that means you use the average value formula. So the word value means y value. If you look at the word velocity, and you're given the word velocity, it means that the y value of the graph will be what you're looking for. And so an average velocity, given that you have velocity because they're the same exact function, the formula I'm going to use, that's the symbol for average, will be 1 over b minus a, and it'll go from a to b of the velocity. So in this case, you'll notice here and here, these functions are the same. That's the only time you get to use an average formula, is when the function you're trying to find the average of is the function that you know, and that's the function you're going to integrate. So in this case, that's the formula. I'll show you how to do it on the calculator in a second. Part B, average acceleration. So we're going from velocity to acceleration, and that's one derivative to get there. What that means is to find the average acceleration, then you would take the average rate of change of the velocity. So the relationship in using the average rate of change is that this has to be one derivative. Okay? So, in terms of finding the average velocity using the calculator, we're going to do, on the calculator, in the blank screen, first thing we're going to do, or not the blank screen, in the y equals, go ahead and put in your function. So right now you should be taking out your calculators very quickly. And then you're going to go on the blank screen, go back to the home screen, and on the home screen we're going to do 1 divided by b minus a. So in this case we want to find it from the interval of, well, I got to give you an interval. So let's do the interval of 0 to 4. Alright, so in this case, I would do 4 minus 0, which obviously you can just put in 4. And that will give you first the dividing by the width, and then we're going to do the fn int of y1, comma x, comma 0, comma 4. Alright, now because you already have the y1 in the calculator, and it's the same function for part B, in the blank screen I can do this whole thing without having to type in or figure out all my values. So on the blank screen for this one, I'm going to put a parenthesis. I'm going to find y1 under vars. I'm going to put in a 4 minus y1 of 0. That's the numerator, divided by 4 minus 0. And so really, this v that's here, we're replacing it with y1 because that's what's written in our calculator. So that will give you the average velocity, average acceleration using the calculator. You actually could do both questions by hand, but I am going to show how to do it with the calculator. In terms of remembering how to know which formula to use. Remember, if the function you're given and the average that you're trying to find are the same function, then you use average value. If the function you're given and the average that you're trying to find is a derivative away, then you use average rate of change. All right. And mean value theorem for definite integrals. So this is one where you're going to end up always finding the average value. You won't necessarily need to know the theorem as in depth as the ones that we've been doing for derivatives. So for this guy here, it says if f of x is continuous on a to b, then at some point in c on the closed interval. So the mean value theorem for derivatives is interesting. You only need it to be closed, and you only need it to be continuous. What it says is the average value, which is a y value, will be within the interval a to b. Another way to say it, the function will equal its average value, which again is a y value, in the interval. That says in. Alright, so that's what it means. Let's see. I think I gave these as just a little bit review of upper and lower estimates. So it's really to start thinking about 5.1 again, because a lot of times we start to forget about old sections. So I use this as a way to kind of bring back 5.1. For 45, you would find your lower and upper estimates. You'll notice that it's a decreasing function, so you'll have to figure out, based on it being a decreasing function, should you use LRAM or should you use RRAM? And then for 46, there's part A, part B, and part C. So again, for each of those, you're going to try to explain, do you have an overestimate or an underestimate? And you'll notice that the function is increasing. Now, I will add a part B for number 45 because you get this a lot in the AP. I would like for you to find the average value on the interval from 0 to 10 using, let's say, an LRAM. Actually, no, I'll make you do one that you haven't done. Yeah, no, we'll do LRAM. And then part C, average rate of change along that same interval of 0 to 10. All right, so one thing I'm going to do is actually go back, because I noticed I do have a little bit of time, I think, and go back to the problem I did with the calculator. I'm actually going to do the same exact problem by hand, just so you see that one more time. So average velocity, because this function and this function are the same, we're going to use this formula here, and we said we were doing this from 0 to 4. So 4 minus 0, integral from 0 to 4 of 4t squared minus 6t dt. So I get 1/4 times the integral of, so f of x, and you're going to evaluate from 4 to 0. So that's the notation I would use. So underneath it now, I'm going to find the antiderivative right here. The antiderivative would be 4t, and then raise 1, divide the whole thing by that same power, minus 6t, raise 1, divide by that whole power. Obviously, it does simplify a little bit. We get 4/3 t cubed minus 3t squared. All right, so we get f of 4, which is equal to, oh, this is just going to suck a lot. I think it's 64 times 4, so 256 divided by 3, which isn't divisible by 3, minus 3t squared, 3 times 16, which is 48. So for now, I'm just going to leave it as this value. And then I chose a better a value, which is 0. Therefore, we get 0 for this. So let me get myself a little bit more space here. Okay, so over here, the average value would be 1/4 times, and f of 4 minus f of 0. F of 4, I didn't simplify it just because I want to make sure that I get this done in time. And then you would have a minus 0 because of the f of 0. So that actually is your average velocity from 0 to 4. It should be the exact value that we found with the calculator. And then to find the average acceleration, here, we would need to find the velocity at 4 minus the velocity at 0 divided by 4 minus 0. So the velocity at 4 would be 64. Actually, I'm going to do this off to the side. I really don't like doing everything in one step because you have a tendency to mess up your minus signs. So just to make sure, velocity at 4 would be 64 minus 24, which gives me 40. V of 0 gives me 0, so I get that the average acceleration is 40 minus 0 over 4, which is 10. So on the left side, the average velocity, if you were to graph the velocity function, so give you a little bit more here to understand it. If you were to graph the velocity function from 0 to 4, which I'm actually going to do, and if we don't have time for this, it means that I want you guys to watch the last part of the video if we don't have time. So y equals 4t squared minus 6t. All right, and then I'm going to graph that. The window of the x's were 0 to 4. And then in terms of the y values, I'm going to look at the table to see what 0 to 4 gives me. So start at 0, go by ones. Let's see what we get. So the smallest value I see is -2. The highest value I see is 40. So just to be safe, let's do -10 to 50. Let's see what that brings us. Did I totally mess that up? I did. I know what I did. There it is. So obviously we don't need -10, so I'll do -5. It didn't go that low. And then that was supposed to be a 50, not a 5. Let's try that again. All right, there we go. So I'm going to seal this over. And I'm going to show you what it actually means in reference to what we've been doing. All right, so this is our function. So the average value, so this is, graphically speaking, this is the velocity, and this is the time. The average value, because this is velocity, it's going to be on the velocity curve. So I'm going to shade in the integral, which would be the net signed area of the velocity. So there's my net signed area. What the average value does is it says there must be a y value, and so if I did things right, this should be 28 over 3, which is about 9.33333. All right, so there's my average velocity. So what that means is, if I remember what I scaled these by, I think I scaled them by 10, 20, 30, 40, 50. No, I did not. Let's go back and see what I actually scaled it by. Window. Y scale was 1. That wasn't very helpful. All right, so if we're going up to 50, 50 is the top. Halfway would be 25. And I'm looking for about 9 point something. So that'd be here. 9.333. So if I was to shade this rectangle, it would be the same as the net signed area of the red. So what you have to understand about the net signed area, which a lot of people get really confused about, this negative piece of the area, however much that is, I'm going to take that away from the red graph. They actually cancel each other in terms of a net signed area. So the blue area would now be the area of the red. They're going to be the same. So the average value was hopefully about 9.33333, which was 28/3. So again, what that means is on the same exact graph, I can look at the area of the red because the yellow negated itself, and the rectangle with the height of that average value, 9.33333. is the same area as the red graph, which is the velocity graph. Now I'm going to erase this all to show you what the average acceleration would be. Average acceleration said that you took the point from the beginning, the point at the end, so that was 0, 0, and that was 4, I think it was 40, and you find the slope. And the average acceleration is literally the slope of the line that connects from 0, 0 to 4, 40, which is 10. This was the velocity graph, and when you take a slope, you always go one derivative down, which is why the slope, it becomes the average acceleration, which was 10. So graphical explanations for average velocity and average acceleration, because we're looking at a velocity graph, end up being very different. So I think that's everything. Again, your homework is number 6, and I will put the key online for you.